Hello, in this video we will be discussing the Reynolds number. This is a very important concept to understand for fluid mechanics because it is often used to determine whether a fluid flow is laminar or turbulent, or it can also be used to ensure that the conditions for dynamic similitude are met. The Reynolds number is the ratio of the inertial forces to the viscous forces acting on a fluid flow. This number, as I said earlier, is used to determine if a fluid flow is turbulent or laminar. So in laminar flow, the layers of a fluid move in straight, orderly paths, and it is caused by the viscous forces acting on a fluid. Laminar flows as opposed to turbulent flow, where the fluid experiences significant mixing and the flow is three-dimensional. And this is caused by the inertial forces acting on a fluid. So here is the formula for the Reynolds number. It is Re equals rho LV over mu, or it can also be written as LV over nu. So Re is going to be the Reynolds number. It is a dimensionless number, so it has no units. Rho is going to be the fluid density. It is going to be in units of kilograms per meter cubed. L is going to be the characteristic length. Also, some people call it the characteristic dimension. The units is going to be meters. And this measurement is, what measurement is used for this is going to be dependent on your application. And I will go over a few of those possible applications in an upcoming slide. V is going to be your free stream velocity, and it's going to be in units of meters per second. Mu is going to be the dynamic viscosity of your fluid, and its units are going to be kilograms over meters times seconds. Nu is going to be the kinematic viscosity of the fluid, and it will be in meters squared over second. And you will use either the dynamic or the kinematic, just depending on which of these two equations you have, and those are going to be dependent on temperature and what your fluid is. We will now go over a few of the different applications and what characteristic length will be used for these applications. So, yeah, as I said, dimension is application dependent. For example, for flow in a round pipe, the pipe's inner diameter will be used. And in this case, the transition from laminar flow to turbulent flow will occur at approximately 2900. Notice once again there are no units for Reynolds number because it is a dimensionless number. So for flow in a rectangular channel, L will be something we call the hydraulic diameter, and it will be 4 times the cross-sectional area of the channel over the wetted perimeter of the channel. And that's going to be the perimeter of the portion of the wall in contact with the fluid, as shown here in this picture. So you'll have your cross-sectional area of your fluid, and then you'll have the perimeter will be made up of this side, and this side. For those of you who are in aerospace engineering students like myself, this is probably going to be the most interesting to us. For the flow over an airfoil or a flat plate, the chord length will be used, which is the length from the distance from the airfoil's leading edge to its trailing edge. And the transition in this case is going to occur around 500,000. And then for shapes such as spheres or rectangular prisms, the diameter or height, depending on the shape of the side of the object facing the fluid, will be used. And in this case, the transition from laminar to turbulent flow will occur at a Reynolds number of 10. So as you can see right here, if this is the direction of the fluid flow, then pretend this is a sphere, then this diameter right here will be used. Alright, so now we're just going to move on to a few examples. So we'll start with a very basic example of flow over a flat plate. So we have air coming in at 20 meters per second, and the flat plate is 1 meter long. So because the air is at 15 degrees Celsius, you can just look up a table and you'll get that the density will be 1.225 kilograms over meter cubed. The dynamic viscosity will be 1.802 e to the negative 5 kilograms over meters times second. We are given that V is going to be 20 meters per second, L is going to be 1 meter. So just plugging into the Reynolds number equation, we're going to get this number right here, which is clearly greater than 500,000. So we know that in this case, the fluid flow is turbulent. All right, so now for a little bit more complicated of an example, we have this example of flow in a channel. So water at 20 degrees Celsius is flowing at 0.25 meters per second through an 8-meter wide rectangular channel. And we are asked what is the highest the water flow can reach for the flow to remain laminar. So what we're interested in this case is this H value right here. And at 20 degrees Celsius, water has a density of 998 kilograms per meter cubed and a dynamic viscosity of 1.003 e to the negative 3 kilograms over meters times second. We're given that V equals 0.25 meters per second. And here, if you remember, the equation for the hydraulic diameter is going to be 4 times the cross-sectional area over the perimeter. Our cross-sectional area, because this is a rectangle, will be base times height. And just plugging in our base, which is known, we get 8 times h. For the wetted perimeter, we have the 2 h's plus the 8 meters down here. And for a rectangular channel or a pipe flow, the transition Reynolds number is going to be 2900. So right here, I just plug in the hydraulic length or the hydraulic diameter equation for L, and then I plug in this perimeter equation we came up with for P to get this. Then just plugging in all of our numbers and solving for H, we get that the height for this, the maximum height that the water can reach and still remain laminar is 0.00292 meters, which is 2.92 millimeters. Now that will be all for this video. One thing I'd like to remind everyone is make sure when you're doing problems such as these that you check the transition Reynolds number for your scenario, because it won't always be a particular number. It might be a range. You might have a transition region is what they call it, where it's not quite laminar but not quite turbulent. And if you have any questions about the characteristic dimension used for your scenario, you can normally just look it up on the internet and figure out what to use. So anyway, thanks for watching this video, and I hope it was helpful, and I hope you have a great rest of your day.